of designing beams last week on Friday. We looked at how to choose an appropriate cross-section, an appropriate commercially supplied beam based upon the cross-section properties. Remember, we introduced the section modulus. We still kind of have that in there. For some reason, we don't actually call it that when we go through this today. But that was a beam design strictly in bending. Now we're going to look at transmission shaft design, which will be a little bit different. A lot of the very same principles apply. However, we don't need the commercial tables like we had on Friday, where we had all those different precast I-beams, channel beams, and all the other types of things. And you can imagine, these were just the tables we had available in the book. There's probably hundreds, if not thousands, of giant catalogs of these things. Transmission shaft design, where we look a little bit at what we saw a couple weeks ago when we looked at the torsion caused by these type of shafts and they're serving their duty. But now we're going to take it a little bit farther, because not only are there the torsional stresses applied because of the power takeoff and power application on these transmission shafts, but there's also bending forces that are a part of this. But we only need to look at the circular shafts. It's very, very rare that transmission shafts are anything but circular. So the way we're going to approach it is, imagine at several places there are gears of various sizes. And we're going to look at the fact that not only is torsion caused at each of those, but there are bending forces, because the torques are applied to those gears by the presence of good old-fashioned forces. These forces being at some moment arm as described by the size of the gear, but then there will be all kinds of forces then that cause bending. So maybe we have something like this. And what this really is, if you look at the gear, any one of the gears themselves, what this really is that we're drawing there is the net force due to the imbalance in tensions on the belts or chains that run around these gears. We looked at that as we looked at the friction in belts last fall in statics class, I hope you remember, where we saw that now that we're really applying much more true applications of these kind of things, we're going to see an imbalance in the forces, the tensions on the two sides. But all I'm drawing on the picture is the net of those. It's actually a T1 minus T2 and applied to the appropriate side. So we'll then take this beam, this transmission shaft, and oh, don't forget, of course, there's some kind of bearing that's stabilizing this, allowing it to spin. We assume no torque of any kind applied at those points. Those are just for stabilization. But we need to look at those because there are forces at each of those as well, which are essentially just the reactions. So if, well, let's put some directions to this. We'll typically take axial direction as the X, and then we have Y and Z directions. And these can be as arbitrary as we need to simplify the problem, especially as you'll see in a little bit. So there's forces at each one of these points where there's a gear. So maybe if I've got some names to these, P1, P2, P3, and a fit of originality. This is still P1 causing bending in that shaft, but because of the moment arm, due to the size of the gear, there's also an applied torque at that spot. And we generally will know which direction, and so we can start putting all these things together. And there's a P2 there as well. And it's causing a torque in the other direction because it's on the other side of the gear, which is trying to twist the shaft in the other direction. And then even another one on P3. This one happens to have a component in the Z direction and will also cause some kind of torque. So take a little time just to draw those in so they're in their general senses. They kind of make some sense with what we're doing. But then each of those will also cause reaction forces of some kind, and those are generally found through the force balance and torque moment balance, just like we were doing all last fall. So they could be in whatever directions they might be caused in. And in fact could be in all three directions, I guess. So that wouldn't be AX, that'd be Z. There, A, Z up there. And this is B, Y. We wouldn't have an X component to any of these. We're not adding axial forces, though we could, if the problem so required it. Now, as we take that same picture and draw it in sort of a planar view, maybe we'll look right down the Z-axis this time. Sometimes it's easier to see what's going on when we do that. I think it is. Helps my small brain in certain ways. So if we're looking right down the Z-axis at a two-dimensional view of this, well, we're not going to see AZ, but we would see AY. And we would see P1 and 2. Whatever those are, however big they are. We wouldn't see P3. It's in the Z direction, but we would see BY at the end there. So clearly I've got the direction on those reactions wrong, but that's part of what we have to fix as we go through the details of the specific problem. But we can see that this looks very much like beams in transverse loadings that would cause certain moments. It would cause the beam to bend in some way, and would then cause some kind of moment with its direction defined by the Z direction using our right-hand rule. We could do the same thing, look down the Y-axis. So that'll give us the Z in that direction. X, remember, axially out like that. And when we do that, let's see, we're looking right down. Now we'd see the AZ. I happen to draw it in the positive z direction, but it depends upon what all these numbers are. P1 and P2 we wouldn't see, P3 we'd see, and then BZ we'd see, but we're looking right down BY, so that wouldn't appear. So again, now we have, again, a very typical type of loading that we've seen before, and we would look at the moment that is caused by those. And this causes a moment in the y direction. We see bending in some particular direction, but no matter which direction it happens to be, our thumb is going to be in the y direction, either plus or minus, for those forces in that particular view. So we've got to put some notion of these things together. So if we look at some arbitrary cross-section somewhere through the beam, look at it in some kind of perspective. So we've got some type of another one of our arbitrary cuts through these things. We're going to see. Don't forget we've got those torsional loads there, so we're going to see some kind of net torsion in this material, the internal forces. But then there's also going to be some net moment in the y direction and some net moment in the z direction, depending upon how all these add up, what all the distances are, all those other things that we've done for problems like that. Now, that might be a little bit of a problem for us because we haven't done any problems that have moments in two different directions. But then the beauty of this being a circular shaft is that we don't need to worry about those because it's just a net moment in one particular direction, which we can easily get from my and mz. By just adding their components together, getting the magnitude of that. And since it's a circular shaft, we don't even care what direction that is in. If we can find my and mz, which are very easily determined by the takeoff forces that we see, then we can very easily do this from that point. So that allows us then to look at this problem in ways we already have. If we've got now some torsion, some net torsion in this shaft due to those gears, the point where power is taken off and power is applied, and we've got some net moment here made up of the two components in the y and the z direction. Then we can do what we've done before, look at a little elemental piece right here at the outer part, because we know that that's where things are going to be the worst. That's the greatest distance. And we can take that little piece and blow it up here for easy viewing. And we know because of the torsion, we'll see shear like that because of the torsion in the direction I happen to pick. And in fact, we know that if we're taking the particular element direction so that the plane of this element is parallel that element is parallel to our net moment, then these are all maximum values. And so we'll have this, the maximum expected shear stress. And for the picture shown, because of this bending moment, we'd have maximum expected shear stress on that face. And since there's no other moment in any other direction, this is the net moment, then we have no, I guess what we call hoop stresses, stresses that go around the piece in that direction. So that would be our element under stress at that point. And these we can find. Remember, instead of the I, the moment of inertia for the cross-section of circular shafts, we use J, the polar moment. No, I guess on bending moment we do use I. It's on the torsion, the shear stress. What symbol do we use for that? We did use C for that as well. Rho, I guess, is for intermediate values. So that'll have J in it there. If you remember, I and J are related anyway by a factor of 2 for circular shafts. So we've got that as a good start. Then we can also finish up what then the maximum, we relate that to the maximum allowable shear stress, and that's the R of Mohr circle for that stressed element as we have there, which you might remember was sigma diff squared. Sigma diff was sigma maximum minus sigma minimum over 2. So that's sigma m squared, sigma m over 2 squared, whereas this is the sigma m up there. I'm just condensing the picture a little bit. And we did that for Mohr circle a bit ago, where this is that thing I invented, tried to patent, couldn't do it, called sigma diff. All right, and we've got those pieces up here. So this is going to be MC over 2I. That 2 on the bottom is from the sigma diff over 2 that we had for the radius, and the TC over J, also quantity squared. And so we relate that to the allowable shear stress. We're almost ready. The complication of this comes mostly just from making sure you've got your views right. You've got your different component directions right. So we can now make this, let's see, we can pull out a J over, or a C over J. Well, let's see, let me make sure where we're going to solve. Yeah, C over J we can pull out. Need to remember that 2I equals J for a circular shaft. So we can just put J right in there over MC. And this then becomes M squared plus T squared. And that C over J is geometry only, cross-sectional geometry only. Very much like what we called the section modulus on Friday when we were doing the beam design. Why they don't call that it here, I don't know. They don't. So then, for our design purposes, we can define that geometry by looking at the loading, the net moment we've got of the two component directions over the torsion at any one place, divided by the allowable shear stress. Okay, so for a maximum allowable shear stress, we want to find the design minimum J over C. Okay, so we're going to do a little bit of a problem here. Most easily done if I give you the problem already in the handout form so you don't have to draw it. What? You'd rather? You don't want one?
I don't want to draw that.
I think that's enough. 1, 2, 3, 4. I think I need one for here. Personally. Okay, what we've got here is a simplified drawing of a transmission shaft. We have a motor that's applying power to the shaft at gear E. The radius of gear E is given, the distance it is from the journal bearing that's supporting it. Then at gear D we have power takeoff. This is gear D is running some other generator or motor or some other thing, but we just simplify it with showing a gear. Don't take it that this business at H just spins freely and doesn't apply any of the forces that we're interested in. That's power takeoff. H is actually running something, but we're not going to show that entire thing. Same with G, and then another gear bearing at A. The radii of all the gears are given, plus their placing along the shaft, so that we can then take that problem and simplify it down to the type of picture we were looking at a little bit ago, where we now have the direction these forces are applied due to the power input here at E, or the power takeoff at C and D, and then the direction, so the implied direction of each of those forces is then available, so we can then apply this this new theory that we've got to a specific problem. Okay, for our purposes, we might want to simplify this drawing even a little bit more. So there's the shaft. We'll take down the shaft as the X direction, and vertical as Y, and out towards us as Z. And so we've got a couple things going on. We have components of the reactions at Z, or at A, so that would be AZ, just following what's drawn, put in the drawing, the directions put in the drawing. We have to find out what those are. Then at gear C, we have a force applied in the Z direction. So what do we, I guess we'll call that Let me keep my notes the same. No, this would be Ft I've got for torsion, so we'll call this the force at gear C. But because gear C has a radius of 60 millimeters, there's going to cause a torsion there, and it will be in the minus x direction. So we'll draw it in so it looks something like that. And it's fairly easy to figure out what those are equal to when we get the rest of the details in here. Then at point D, we have another force coming off of that gear as we have power takeoff. But that's also applied at a moment arm by the gear size. So there'll be a torsion in the same direction as there was in gear C. And then gear E, due to the placement of where the motor happens to be on that, we'll have a force in that direction. That's Fe. And there it is. I'll show you how we get that in a second with some more of the details of the problem. And then it's got an applied torsion in the other direction. And then we have the two reactions at B. Again, assuming no axial load. Okay, for this problem, and this is what leads to the force being exerted by the motor that's turning the shaft, we've got an expected frequency in the shaft of 480 RPM, which is 8 hertz. Everybody knows what a hertz is? Everybody know what a hertz donut is? Pow! Hertz donut. Oh, David, you like that one? David and John liked it. Nobody else liked it. You two are now my favorite students, far and away. Yeah, there aren't many engineering jokes, so that's...
So it would be a kilohertz.
You kind of have to collect them. What?
The megahertz.
Yeah, megahertz.
Kilohertz donut.
Yeah. Yeah, you can escalate this as almost all warfare can be. So the power being applied at point E from the motor we'll take to be 30 kilowatts. Power takeoff at G is 20 kilowatts and at H 10. So that kind of balances. That not H, C. What do I have for G and C? Where do those come? Oh, that's from the upper gone. That's the power takeoff here at H and at G. So 30 kilowatts coming in on the motor, and we're using it all. We're assuming no losses in that way. So the other piece we need is an allowable shear stress based on the material of the shaft, whatever that might be. We'll take that to be 50 megapascals. Okay. And then, if you remember when we were doing these type of transmission shafts earlier, when we were just looking at the pure torsion, we can relate the power to the frequency and use that to find the torsion in each of one of the places. So we know at E there's 30 kilowatts coming in. We know the rotational frequency of the shaft. We can then find the torque being applied at E as the power comes in, the 30 kilowatts. then 20 and 10 take off at C and D. The applications were named G and H in the picture. Okay, gear C has takeoff G, gear D has takeoff H. If that doesn't suit your fancy, feel free to fix it or change it a little bit. But that allows us to find these two torques by simply applying this there. And that's then how this 3.73 was figured out. Know the torque at E, know the radius at E, and then find the force at E. Because we know the radius of that gear. That's given there, the 0.16 meters. Okay, so we can do that for each of the pieces. I won't force you to do it on this one. You can on the next one, but these values come to be let's see, AY is 0.932 kilonewtons. AZ is 6.22. Oh, I have enough room to squeeze all this. Oh, that's just the reaction I need to fit in here. And both of these are 2.8 kilonewtons on the other end. And we'll put the forces and the torques in a slightly different drawing as we put this together, because we're going to do it this way. All right. So let's look at the y-x direction. Just make it a two-dimensional picture. Let's see. In the y direction, we've got this 0.932 at the reaction. The force at C we don't see because it's a z force and we're looking down the z-axis. Same with D, so we're going to only see the one at E, which will be something like that, and we know that to be the 3.73 kilonewtons. Remember, that's from finding the power coming in, the known frequency, figure out what the torque is applied at E, then from that torque and the radius of the gear, find out what the force is. Sorry? And then the 2.8 due to the reaction By. Bz we don't see in this view. What we're looking to do, remember, is to figure out what the net moment is in the y direction. Sorry, this will be the z direction. If we get moments, they'll either be plus or minus z. And then we're going to do the same thing for the other view, and then the two of those will give us the maximum possible moment. So we'll have to put a couple of these pictures together. So let's figure out what the moment is at different places in the z direction from this drawing. So this will give us m, not my, mz in kilonewton meters. And this is nothing more than we've done before. This looks very much like some problems we did in statics last fall. We had some transverse loadings on a beam, and that then allowed us to draw the moment diagram, doing exactly the same type of thing we've done before. So let's see, because the two ends are simply supported with just journal bearings that can maintain no moment, no significant moment, we know that the two end moments are 0. And the only place we have any transverse force being applied is 3.73 kilonewtons, and that will have a moment arm all the way down of what was it, 20.6 or something? I think when we got there. So we'll have then a maximum expected moment there of 560. And you get that just by doing an imaginary cut just barely before this 3.73, so that we know we have 0.932 there. We must have a shear of 0.932, and then we have that distance between these two as a couple. So that should be the 0.932 times, what is that, 600 millimeters. So that's how we got that. So hopefully no great mystery. Since there's no load in between, we know that that's just then a linear connection. So there's our moment diagram for this view. And we see obviously in this direction the worst spot is on that gear E. But it allows us to also find the values at gears C and D. We can then take these values, add them to the values we're going to find at C and D in the other direction, and that will tell us which one of those points along the beam is the worst case. So right now it looks like gear E, but we have to check the other two directions. So I'll try to squeeze that in the bottom here. So they're right above and below each other. Tends to be a little more convenient, I think. So here's our shaft. Already deforming. Look at that poor thing. Yeah. We can't have that go out in public. A little bit better, I guess. All right, so this is our ZX view. We're now looking right down the y-axis. So we see AZ coming in. And that happens to be 622. You know, when you find that, remember, from the force and moment balance on the shaft itself, just like we were doing last fall. We see FC due to the takeoff, and that's 6.63. And remember, that comes from the power takeoff, 10 kilowatts at that frequency, and then that'll allow us to get the force there. FD, we see it's in the same direction. Its value 2.49. All of these numbers are kilowatts here. 2.49. I want to zoom in on some of these numbers if they're not showing up right.
They're showing up.
Okay, good. And then, let's see, E, since we're looking right down the y-axis, we don't see that force. We don't see By, but we do see BZ. And its magnitude comes out to be 2.9. And again, all of these are kilonewtons. So kind of squeezed it in there. This is happening at the same time as our previous drawing. It's just a different view of it. And then we can draw the appropriate moment diagram for this one as well. And then we can put the two together. We can put the two together. Sorry, this should be MY. We'll put MZ and MY together in at least the three obvious places where the three gears are, and then make our estimate for what the total moment should be. Remember, we're going to combine the components MZ and MY to get M, and then we put that in there in the equation. All right. No moment at the two ends. Those are simple journal bearings. They don't really support any moment. And so we can get then, knowing we have this 6.22 over this first 200 millimeters would give us a moment of, did you hit it, John? Oh, sorry, but this 560, I just noticed, should be not kilonewtons, but newtons. So this will be newtons per newton meters as well. So did everybody get this unit change here on the moment diagram? This 560 is newton meters, not kilonewton meters. All right, so if we figure out the moment's going to linearly increase up to 1244 at gear C, then it's going to decrease linearly, and you can figure all this out just from the way we used to do our moment diagrams. That decreases to 1160, and it's linear in between, so we can draw those. And then it goes down to actually at gear E, it's about 580. And a linear decrease in between. Let me change the slope a little bit just so it's a little more accurate. I don't know how much difference that makes. So there's our two moment diagrams in perpendicular directions to each other. What that allows us to do is to compare the, vectorially add the moment, the M moment in the Z direction at gear C with the moment in the Y direction at gear C. Also do that at gear D and do it at gear E. Because you notice, without looking at both directions at once, we wouldn't know which one of those spots is going to give us the worst case moment in across the beam. We also need to look at the torsion in the beam, and that I can drop right below this picture. And that we don't have to do in a particular direction because the torsion is all in the x direction. So that diagram comes out to look something like this. What are the units on this one? Also Newton meters, so that everything will go together well in this equation as we figure out, actually we're going to use this one, figure out the allowable cross-section properties. So when you look at the torsion in this direction, there's none in this first part between A and C, because C is just, point A is just freely turning in the bearing. So we don't have any torsion until the second part. That's 398. Then it jumps up to 597. And then it goes back down to 0 for the rest of the beam. So that allows us to look at where these worst case possible situations are, where the M and the T squared are the greatest maximum maximum concern. Oh, where do I want to clean up here? We'll put it here. You've got this. We're going to finish that up in a second. I definitely want to keep those. For reference, C, B, and D, so I don't lose those. A and D is my reference numbers. Okay. So we want to compute then this quantity M squared plus T squared, which equals M y squared plus mx, not x, z. Remember, those two together, we're calling this just a simple m, the net moment. And then we do this for each of the 3 spots to figure out where the worst case scenario is, where the moment plus the torsion together are the worst possible situations. So we do that for each one of those. Gear C, we get, and this actually we could call a moment if we want, I guess. But just putting the values in. For gear C, these intermediate values, let me give you those. I think I have them on here, did I not? Yeah, I didn't put them in yet. This is at 186. That's just the 560 that we found and then a straight line drawn back. 373 here in gear D in that view. And then, oh, I've already got the other view labeled, so we're okay with that. All right, so let's put this together. Make sure we got the calculation right. At gear C, MY is 1244. At gear C, MZ is the 186. Remember, that's M squared equals MY squared plus MZ squared. That's all we've done right there. And then we add on the expected torsion, which is the 398. And that quantity equals 1319 Newton meters. Do the same thing for gear D, and then again for gear E, so we can find out at which point are things the worst. So at gear D, MY is 373, MZ is 373, MY is 1160. So 373 squared plus 1160 squared. I don't know, to my mind, this really helps doing this. Having to do this step explains why these different views are so useful. And then at gear D, we have an expected maximum torque of 597. And that's then 1357 Newton meters as the expected total torque at that place. Moment. Obviously, gear D is a worse spot than is gear C. And that would not have been obvious if we hadn't done all three of these different steps. I don't think. What? Yeah. It would have been very tempting to see that and stop there, or see this and stop there, but we've got to check the entire beam. So then here E, we have a 560 and a 580. So each of those squared, and then a 597 squared. Remember, on the torsion, it takes a jump right at each of the gears, so we use the worst value at that gear as a spot. So turns out this is 1103, so much less. Our biggest concern is at the 1357.
You said 11?
Sorry?
You said 1103?
1003. I probably said 11, yeah. So our worst situation is at D. Actually, it's probably somewhere either side of that. We have to actually look at intermediate values to see which one of these is the worst case. If we go to the right of gear E a little bit, all of these start to drop. If we go to the left of gear E, actually gear D is our worst one. If we go to the right of gear D, we have the highest torsion, and as we go to the right, MZ increases, but MY starts to decrease a little bit. So we have to look into all of those possibilities, but this certainly looks like the worst case. The worst situation there. We'll have the factor of safety on it, but it allows us now to figure out the minimum section modulus, J over C, using this value. Call it maybe MD, the total torque, total moment at D. And so that's the 1357 we found here, divided by the allowable stress, I've erased that, 50 megapascals. And then from that you can figure out what the radius should be. Where can I squeeze that in? Put it up here. Because this will now give us the radius. G over C is pi over 2c cubed, and then we can find that radius C. Remember, that's just J over C simplified a little bit, and we know that that now has a limit on it. of this value, 27.1 times 10 to the negative 6th. Meters cubed, where that value is just finishing that ratio, G over C. And so now we can solve for C. As 25.8 millimeters. That's the minimum, so you go to 30 maybe, or 35 or something, or maybe a factor of safety needs to be applied here. One or the other. Is that enough for the first hour of the morning? No, it's not enough for today.
That was fun.
That was fun? Good. Now you get to do it on your own. Alright, but before I clean up, any questions? So we'll just take the two different 2D views, figure out what the moment diagrams for there are, and then add the torsion, and then each place then figure out what those three do to combine the internal forces of the shaft.
And C gives us radius.
And then, yeah, C is the radius. Remember, that's our symbol for the maximum dimension in the cross-section from the neutral axis, which is, of course, since it's circular, right down the middle. C takes us right out to the outside, because that's where the things are the worst. That's the worst case. All right, fair enough? Go. You ready to go at it?
What's a factor of safety
Bring it on.
for something like this?
I'm not real sure. I've never designed transmission shafts, but I figure it's probably 2 to 3, which is fairly typical. Joe, question?
How good the torque?
Here?
Pretty big shaft.
No, the
Here?
yeah.
Oh, we do a balance on these two using just these torques. So let me show you how those come about. If we look at just some segment from A, not quite up to point C, put our imaginary cut. Here's A right there. Point C is out here somewhere. This journal bearing, it's just a freely spinning bearing, and it keeps the shaft from flying around, just supports it, but it doesn't apply any torque. So we know between A and C, there is no internal torsion. So that's just that. Then we take it a step farther, go past C but not up to D yet, and put our imaginary cut. So C is right here, A is right there, and the torsion due to point C, and remember that's using the amount of power taken off there, the frequency, and we can find T there. Just do that for point C. We know how much power was coming off. I think it was 10 kilowatts. The frequency, I think, was 8 hertz. Remember, watch your units on these. So it means that
20 kilowatts for that.
there's TC there. There must then be an internal torsion of the same amount, all the way between C and D. So that's why it's constant there. There's no other power being taken off or put on. And then we do the same thing one more time. Past D, C, we know to have that much torque. D was in the same direction. Oops, I don't know why I drove that direction there. I already know the direction up there. So just swap those directions around. And those two added up then must be counterbalanced by the internal torsion in the material there. And so that's what this diagram is there. So this 597 is actually the 398 at C plus whatever the difference was at D. It looks like it's about 100, 200, 199. Okay, that help? Phil, all right? Chris, comfy? Tommy, you on board? Okay. One for you to do. All right. So. Here's our shaft. We've got two 50mm radius gears. One there. And one there, equally spaced, 1/3 of the way each along the shaft. Beautiful. We'll put a direction on this. Z, Y, and X. Okay, 300mm between each of the major points here. So all dimensions in millimeters. 50mm gears, both. In radius. And known forces, this is a tension imbalance in the chain, if these are gears, or the, boy, my perspective is all off on this, that's terrible. Those gears should have been seen from the other side. And, oh my goodness, it's not going to work. I can't put in a.
You can always think of it as being viewed from the bottom.
What?
You can always think of it as being viewed from below.
Well, not now. Now I erased it. I guess, yeah, I guess I could have put. No, I still would have made the wrong direction. That's okay. You're all taking notes in pencil. What do you care? Told you to use chalk. You won't do it.
I don't think chalk goes very well on paper.
Tell that to some of the great artists in the world. If you can use chalk on sidewalks, you can use chalk on paper, I always say. Okay, there we go. So now we've got that force going in there, also 5 kilonewtons. Alright. Doesn't matter, it's a lot easier than if you take these in the side perspective, so we can do that together if that would help. So in the XY direction, remember, turn this force into a force and a moment, but we have a minus y direction force of 5 kilonewtons. And then don't forget, you need to figure out what the supports are. So we'll call this A, B, C, and D. A, B, C, and D. So this is ND. There's end A. This is the force at C. And there is no other y force seen in this xy view. And so now you can figure out what the two reactions are. Not A, D, A, D, Y. And then again, in the z direction, in the xz plane, we see nothing at C. At B, we have a minus z force. Again, of 5 kilonewtons, and then that'll allow you then to find a z and dz. And then don't forget, you also need to find how much moment is applied at those gears by the two of those. In the same way that we did with the other drawings. And then you want to do the moment. Well, it might be easier if we keep them in the same direction. Find the z moment. The y moment. And then the torsion at each of those gears. Remember that these are 50 millimeter in radius gears. We'll do it in kilonewton meters, so we can all easily compare numbers. I think you have all the pieces then. Yep, I think everything, oh wait. I need an allowable shear stress. Same one as we just had, I think, 60 megapascal. Okay, so you don't have to use the power requirements and the frequency on this one. I already gave you the force. So don't forget to figure out what the torsion is for each of those so that you can complete the drawing. So this is point B, C, D. Okay, so let's see if we get the same thing right. So the first thing you need to do, figure out the reactions, figure out the torques at each of those places. It's just the 5 kilonewtons times the 50 millimeters. In fact, that's a no-brainer. I'll just give that to you. 0.25 kilonewton meters. And then at D, it's the other way. take any force and replace it with a force and a moment, which is exactly what we're doing at the gears. And it's the same in either view, it's not a different view for the torsion, because that's in the x direction. All those torsions are either plus or minus x, so they appear in either view. All right, everybody got a picture of what we're doing? No, David doesn't have a picture either. Okay, and that 0.25 is just the 5 kilonewtons at 50 millimeters moment. Phil, make sense? Comfortable? Tommy? Okay, so come up with these drawings here where we show the torque, the moment at different places. I think it's a little easier making them above and below each other. Just a little bit less chance of making errors. Remember, for the moment diagrams, the torsions don't apply, and then for the torsion diagram, the moments don't apply. Isn't that all right? Thinking. Do what? Did you? For these two moment diagrams, only these forces apply, because that's what's causing the bending. These are torsions which do not appear in the moment diagrams. Those torsions apply down here, the applied torques only apply down there. Joe?
Second one?
Oh yeah, that should be a B, sorry. Yeah, A, B, C, and D. Okay, thanks, Joe. Captains of industry after this. You can now build water wheels, start your own corn grinding business. Make $1 million until the Revolutionary War comes along. Messes everything up for you. You feeling it, Joe? Okay, check these as you go along, make sure you're getting it, because if you get these, not only these drawings, but these values wrong, you're doing a different problem. So check them as you go along with each other, or with me.
Did you get reaction?
You come on, David, I can't help you check.
More sig figs. We love sig figs.
That's just calculated as.
I know. We'll take that down to the machine shop and expect them to do something with that kind of precision for you. They'll try and then charge you $5 million for the part. Because they'll do what you say. Actually, what they'll do is if they got a number like that, the first thing they do is call up your boss and say, how long has he been working here? It always just right out of school. They say, okay, send him down. Because they've seen it before. They've seen somebody send in a specification with 15 sig figs.
Yeah.
The first thing they know is this is somebody right out of school. Tom, do you agree with somebody?
So far with the reactions.
Okay. What's appropriate? Most everybody's getting it. So, I have, let's see, in the Y direction. Make sure I've got the right order. MY. Okay. We only have bending moment for this one, and I believe it's 1.0. No moment at the bearings. I didn't even draw the bearings yet. And so just by symmetry, that puts this at 0.5. That's kilonewton meters. Is that what you got? And then actually just the opposite for the other one, because we have a fairly symmetric picture. That the picture you got for those two? No, Samantha? What was different? Values? Well, the reactions, let's make sure, I guess you got those. This one, AZ, I have is 3.33 kilonewtons, and AY is 1.67. Does that look right? And then, yeah, it's just the opposite on the other ones. 3.33 there. And 1.67 there. So then the moment here is the 333 times the 30 millimeters should give you 1. And then the torsion, we only have that one bit in between, so it's pretty simple. Two far ends are free to turn. So you really only need to do one place to do the symmetry of the problem. The 1 and a 0.5 and a 0.25, because you get the same thing at the other gear. You're going to get exactly the same values. And so then you can finish that bit. And you should get a diameter, then we're right at the end. Diameter of, and you round it up to the nearest millimeter probably, 46 millimeters. So we're at the end there. If there's any troubles, we'll check them on Friday. Or you can come see office hours. But remember, it's the square root of that squared plus that squared plus that squared.
Why don't you take the middle?
Oh, here? Yeah, well, you check that. What you probably get is when you look at that thing as a whole, you've got these 2 points, you figure it does something like that.